Section: Introduction. In this section, we discuss Supervised Fine-Tuning, SFT, a common method for adapting large language models, LLMs, to new tasks by training them on expert demonstration datasets. SFT is popular because it is easy to implement and quickly helps models mimic expert behaviors. However, we note that SFT often struggles with generalization compared to reinforcement learning, RL, methods, which use explicit rewards to explore various strategies and achieve better generalization. Despite its advantages, RL can be resource-intensive, sensitive to hyperparameters, and dependent on reward signals, which may not always be available. Even when RL is an option, SFT can quickly capture expert behaviors that RL might miss. To combine the strengths of both methods, many hybrid approaches have emerged, but we question whether we can fundamentally enhance SFT itself. This is important because SFT is the only option when there are no negative samples or reward models available. We aim to fill this gap by analyzing the differences between SFT and RL mathematically. We show that the gradient update in SFT can be seen as a specific case of a policy gradient method with a unique, implicitly defined reward structure. Our analysis indicates that this implicit reward is very sparse and inversely related to the probability assigned to expert actions. This leads to a problematic reward structure, especially when the model gives low probabilities to expert actions, resulting in high variance in the gradient and a challenging optimization landscape. To address this issue, we propose dynamic fine-tuning, DFT, which modifies the standard SFT objectives by rescaling them with token probabilities. This adjustment neutralizes the inverse probability weighting that causes the problematic reward structure and high variance. Our approach transforms the gradient estimator into a stable, uniformly weighted update process. Our empirical results are significant. For instance, when we fine-tune the QWEN 2.5 math models on the Numina math dataset, our method shows improvements that are several times greater than those achieved by SFT. Importantly, while SFT tends to underperform on difficult datasets due to overfitting, our method consistently provides substantial improvements, demonstrating better generalization. We validate these results across different model types and data sizes. We also explore how our method performs in RL scenarios where negative samples or dense reward signals are present. Our experiments reveal that DFT not only outperforms other offline RL methods but also competes well against online RL methods, all while being simpler in terms of computational resources and procedures. To understand how DFT affects the model, we analyze the changes in the probability distribution after training. We find that traditional SFT training tends to increase token probabilities uniformly, while our approach interestingly pushes some token distributions away from the training set. We discuss this phenomenon in detail later. Our contributions are both theoretical and practical. Theoretically, we establish a mathematical connection between LLM SFT and RL, identify the reasons for SFT's limited generalization, and propose a method to enhance it. Practically, we demonstrate that a simple adjustment can significantly improve SFT's performance and generalization across various tasks and models. Section Summary. In this section, we discuss the limitations of supervised fine-tuning, SFT, in generalization compared to reinforcement learning, RL, and propose dynamic fine-tuning, DFT, as a solution to improve SFT's performance by addressing its ill-posed reward structure. Our mathematical analysis reveals that DFT stabilizes the gradient updates, leading to significant enhancements in model performance and generalization across various tasks without requiring external feedback. Section: Method. In this section, we describe our method, which consists of two main parts: supervised fine-tuning and reinforcement learning. We denote our expert demonstration data as a set of pairs, where each pair consists of a query and its corresponding expert response. When we sample a response for a given query from our model, we refer to it as a response from the policy. To connect supervised fine-tuning, SFT, with reinforcement learning, RL, we rewrite the SFT gradient using importance sampling. We introduce auxiliary variables to compare the expert distribution with our model's distribution. This allows us to express the SFT gradient in a way that resembles the policy gradient in RL. We find that traditional SFT acts like an on-policy gradient, where the reward indicates whether the model's response matches the expert's. However, the importance weight can lead to high variance in reward estimates, especially when the model assigns low probability to the expert response. This high variance, combined with the sparse reward signals, can cause the model to overfit to rare exact matches, limiting its generalization. To address the skewed reward issue, we dynamically reweight the reward by using a corrective ratio based on the policy probability. This results in a new gradient that we call dynamic fine-tuning, DFT. We ensure that gradients do not flow through the reward scaling term, simplifying the loss to a reweighted form. However, calculating importance weights over the entire trajectory can lead to numerical instability, so we apply importance sampling at the token level, similar to methods used in proximal policy optimization, PPO. This adjustment allows the DFT loss to provide a uniform reward for all expert trajectories, promoting stability and better generalization. In our main experiment, we focus on the standard SFT setting, which relies solely on expert demonstration data without negative samples or additional signals. Our expert dataset comes from various sources, including expert models and human annotations. We aim to evaluate whether DFT can consistently outperform standard SFT across different tasks, model architectures, and dataset sizes. For our dataset, we utilize the Numina MathCot dataset, which contains around 860,000 mathematical problems and their solutions. We randomly sample 100,000 instances for training, as this is sufficient for our evaluation. We conduct experiments with several state-of-the-art models, including Qwen 2.5 math and Llama models. In terms of training details, we use the Virl framework and follow recommended SFT hyperparameters. We employ the Atom W optimizer with specific learning rates for different models and set a mini batch size of 256. The learning rate follows a cosine decay schedule, and we also include a comparison method called importance-weighted SFT, IWSFT. All training settings align with those in the original paper, with the exception of setting the number of training epochs to 1. Section Summary. In this section, we describe our approach to fine-tuning models using supervised learning and reinforcement learning, highlighting the challenges of reward sparsity and variance in standard supervised fine-tuning, SFT. We propose a dynamic fine-tuning, DFT, method that adjusts rewards to improve generalization and stability, and we outline our experimental setup using the Numina MathCot dataset to evaluate DFT against traditional SFT across various models and tasks. Section: Evaluation Settings. In this section, we evaluate mathematical reasoning tasks using established benchmarks such as Math 500, Minerva Math, Olympiad Bench, AME 2024, and AMC 2023. We apply the default chat template and chain of thought prompting to encourage step-by-step reasoning in each model. Our results reflect the average accuracy from 16 decoding runs, using a temperature setting of 1.0 and a maximum generation length of 4,096 tokens. Our main findings show that DFT consistently provides significant performance improvements over base models when compared to standard SFT across all evaluated large language models, LLMs. For instance, with Qwen 2.5 Math 1.5b, DFT achieves an average increase of about 15.66 points over the base model, which is more than 5 times greater than the 2.09 point improvement from SFT. This trend is evident across various model families and sizes. Llama 3.2-3b sees a gain of 3.46 points with DFT, surpassing SFT's 2.05 by about 1.4 times. Llama 3.1-8b achieves a 10.02 point increase with DFT, compared to SFT's 5.33, which is nearly 1.88 times higher. DeepSeek Math 7b improves by 15.51 points with DFT, 1.58 times greater than SFT's 7.18, and Quen 2.5 math service gains 15.90 points. DFT shows strong generalization and robustness, particularly on challenging benchmarks where SFT often performs poorly. For example, on Olympiad bench, SFT reduces accuracy for Quen 2.5 Math 1.5b from 15.88 to 12.63, while DFT increases it to 27.08, an 11.20-point improvement over the base model. On AMI 24, SFT decreases accuracy for Quen 2.5 Math 7b by 4.20 points, whereas DFT raises it to 8.56, achieving a 1.88-point gain over the base model despite the benchmark's difficulty. A similar pattern is observed on AMC 23, where SFT lowers Quen 2.5 Math 1.5b's performance from 19.38 to 18.75, while DFT boosts it to 38.13, a gain of 18.75 points over the base. For Quen 2.5 Math 7b, SFT shows only a slight improvement of 1.86 points, while DFT achieves a 17.04-point gain. These results highlight that DFT scales better across models of different capacities and is more resilient on tough reasoning tasks where traditional SFT struggles, indicating its potential as a more effective fine-tuning method for enhancing mathematical reasoning in LLMs. We also observe that DFT demonstrates better learning efficiency and faster convergence. Our analysis reveals distinct differences in learning dynamics between DFT and standard SFT on Quen 2.5 Math 1.5b across all math reasoning benchmarks. Compared to SFT, our method has three key advantages. 1. It converges faster, reaching peak performance within the first 120 training steps on most benchmarks. 2. It shows better early-stage performance, outperforming the best final accuracy of SFT within the first 10 to 20 steps. And 3. It is more sample efficient, needing fewer updates to achieve optimal results. This quicker convergence suggests that DFT's dynamic reweighting mechanism leads to more informative gradient updates, guiding the model toward high-quality solutions early in training. It also helps avoid optimization plateaus or noisy regions that standard SFT often encounters, allowing for more efficient learning of complex mathematical reasoning patterns. Furthermore, DFT outperforms the concurrent importance-weighted SFT, IWSFT, in most settings across model families and benchmarks. Our results show that DFT achieves higher average accuracy than IWSFT on most model families, including Llama-3.2-3b, Llama-3.1-8b, DEEPSEEKMATH7b, and Quen 2.5 Math 1.5b. Although IWSFT slightly outperforms DFT on Quen 2.5 Math 7b, this improvement is not consistent across datasets. In fact, IWSFT shows limited robustness, underperforming compared to standard SFT on Math 500 and AMC 23 for LLAMA 3.2 to 3b, and on Minerva Math and AMC 23 for LLAMA 3.1 to 8b. These instances indicate that IWSFT may struggle to generalize beyond specific training signals and can even degrade performance on harder benchmarks. In contrast, DFT consistently improves upon both the base model and SFT across nearly all datasets, including those where IWSFT fails. This emphasizes DFT's superior generalization ability in diverse mathematical reasoning scenarios. Additionally, IWSFT incurs extra computational costs by needing a separate reference model to compute importance weights, while DFT dynamically derives its own weights from the model's token probabilities, leading to a more efficient training process. Section Summary. In this section, we evaluate mathematical reasoning tasks using established benchmarks and demonstrate that our dynamic fine-tuning (DFT) method significantly outperforms standard supervised fine-tuning (SFT) across various models, achieving higher accuracy and faster convergence. DFT not only enhances performance on challenging benchmarks but also exhibits better learning efficiency and robustness compared to both SFT and importance-weighted SFT, IWSFT. Section: Data Preparation. In this section, we conduct an exploratory investigation into applying DFT in an offline reinforcement learning setting, which helps address the issue of sparse rewards compared to the Supervised Fine-Tuning, SFT, approach. We utilize the Rejection Sampling Fine-Tuning, RFT, framework, sampling responses for 10,000 math questions with a temperature setting of 1.0, generating 4 responses for each question from the base model. We identify correct answers using a math verification process, resulting in about 140,000 training examples. For DPO training, we create 100,000 pairs of positive and negative preferences from these responses. All our experiments use the Quen 2.5 Math 1.5b model. We compare DFT with various offline reinforcement learning methods, including DPO and RFT, as well as online methods like PPO and GRPO. The training setup for RFT and DFT follows the configuration outlined earlier. For DPO, we apply the Ms. Swift framework with a learning rate of 1 millionth, a batch size of 128, and a warm-up ratio of 0.05. For PPO and GRPO, we use the Verl framework with the same learning rate, a batch size of 256, and a warm-up ratio of 0.1, setting the number of responses per input to 4 for GRPO. Our results show that DFT performs best in the offline reinforcement learning context, surpassing both offline and online baselines. Specifically, DFT achieves an average score of 35.43, which is 11.46 points higher than the best offline method, RFT, and 3.43 points higher than the strongest online algorithm, GRPO. Our model excels across all 5 benchmarks. For instance, on Math 500, DFT scores 64.71, slightly ahead of GRPO and significantly better than PPO and RFT. The improvements are even more pronounced on tougher benchmarks like AMC 23 and Minerva Math, where DFT outperforms GRPO and RFT by substantial margins. We also compare our method with the IWSFT approach in the offline setting. While IWSFT performs well on some datasets, its overall average score is still lower than ours. Additionally, IWSFT shows only slight improvements over its performance in the standard SFT setting, contrasting sharply with the significant gains achieved by DFT. These findings indicate that IWSFT struggles to effectively utilize reward supervision in offline scenarios, while DFT consistently translates these signals into better generalization and task performance. This highlights DFT as a straightforward yet powerful fine-tuning strategy. Furthermore, we analyze the token probability distribution of the model trained with DFT compared to standard SFT and other RL methods. The results show that SFT tends to increase token probabilities uniformly, mainly affecting lower probability tokens, while DFT creates a bimodal distribution, boosting some token probabilities significantly while suppressing others. Other RL methods exhibit similar trends, but to a lesser extent. We find that the lowest probability tokens are often conjunctions or punctuation marks, suggesting that for effective learning, models should not aim for uniform confidence across all tokens. Instead, it may be more beneficial for large language models to focus on substantive content rather than grammatical tokens, akin to how students are taught to prioritize important concepts over minor details. Section Summary. In this section, we explore the application of DFT in an offline reinforcement learning setting, utilizing rejection sampling fine-tuning to generate approximately 140,000 training examples from math questions. Our results indicate that DFT outperforms both offline and online RL methods, demonstrating superior performance across various benchmarks and suggesting it as a more efficient alternative to traditional RL approaches. Section: Training Hyperparameters Ablation. In this section, we evaluate the robustness and sensitivity of our approach, DFT, by conducting an ablation study on key training hyperparameters, specifically learning rate and batch size, using the Quen 2.5 Math 1.5b base model. Our analysis seeks to answer two main questions. 1. Is the performance difference between DFT and SFT due to poor hyperparameter choices in SFT? 2. How sensitive are both methods to changes in learning rate and batch size? We test both DFT and SFT with 4 different learning rates: 200 thousandths, 100 thousandths, 50 thousandths, and 10 thousandths. Our results show that both methods are somewhat sensitive to the learning rate, with DFT consistently outperforming SFT across all settings. This indicates that the performance gap is not solely due to suboptimal hyperparameters in SFT. We find that intermediate learning rates, specifically 100 thousandths and 50 thousandths, yield the best results, while both lower, 10 thousandths, and higher, 200 thousandths, rates lead to noticeable declines in performance. This underscores the need for careful tuning of the learning rate in gradient-based fine-tuning. Next, we examine the effect of batch size, testing values from 32 to 256. Our findings reveal that both DFT and SFT maintain relatively stable performance across all batch sizes. Although we observe some minor fluctuations, there is no clear trend showing that larger or smaller batches significantly impact final accuracy. This suggests that batch size is not a critical factor for either method in this context, and using default values may be adequate in practice.